Happy Sunday. This is PFG.Live, the podcast dedicated to the writings of internet philosopher Hey Man, why didn't you? Hey Man, why didn't you use the RASP file instead of those PFG Stones? Welcome aboard. We've got a great crowd in Discord and a bunch of folks checking in on YouTube. Let's see. We have, well, I'll tell you who's in Discord. We got Unix Carbide, Dale, Josh, Robin, Mayek, Carl Tauber, Ted Hyde, Plate Pringler, nice to see you, sir, Evils, AJF, Jeff, and Orjan. Welcome aboard to you alls. Let's see, on the YouTube side, we're getting weather reports from Machine Creation, who says it's 26 Fahrenheit in the high mountain deserts of Idaho, and everything is covered in hoarfrost. Thank you, Wes. Let's see. John Thawley says it's 77 degrees Fahrenheit, sunny and clear in Southern California. Perfect paint stripping weather. Absolutely is. Dave G says it's 16 degrees with a pressure of 30 inches, dew point 8 degrees Fahrenheit. 8 degrees Fahrenheit in Northwest Ohio. Let's see, Evils is checking in from Ghent, Belgium, and he says it's 21 degrees in here. What's your problem? Plate Pringler. Do I have to pronounce that correctly? Plate Pringler is here, and he says it's 35 degrees and sunny in Strasbourg. Josh says in a mild-weathered Winnipeg at Charlie Yankee Whiskey Golf, it is winds 330 at 29 knots, visibility 1 mile. The runway 36, variable visibility from 2,400 to 2,600 feet. Golly. A bunch of other runway information in light snow and blowing snow and a vertical visibility of 600 feet. Stay inside, get under the blankies. Dale at Widgetworks says it's minus 11 degrees science, 13 degrees Fahrenheit, and cloudy in the far north Midwest. Unix Carbide in the Brooklyn, New York says it's 34 Frankenstein and foggy. Less than 10% relative humidity in the filament chamber, however. Excellent. Protein Machining, wait for it, says it's 71 degrees Fahrenheit, 15% relative humidity in sunny Arizona, and we don't know what snow is. Welcome aboard, sir. Let's see, bouncing back to YouTube. Kevin Blodgett is with us. Welcome aboard, sir. He says it's 56 degrees Fahrenheit, severe clear in Portland, Oregon. That's nice to hear. A little bit of a change. And for you guys, here's a picture outside my front door where it is very much wintry. It's rather nice. But we have currently 33 degrees, 83% relative humidity. The snowometer this morning registered, do I have a snowometer picture for you guys? Sure I do. The snowometer registered 3 inches of snow, total storm accumulation, and we did a reset. And by we, I mean Honorable Wife did a reset, and we are now ready to go for the next input. Ted Hyde is with us. And he reports from Kilo Lima Echo Echo, winds are 340 at 9, gusting 23 knots, 4-mile visibility, light rain and mist, few clouds at 1,000, broken at 3,900, overcast at 4,500, temperature 09, dew point 08, altimeter 3011. Remarks, need more lab ants. You shall have more lab ants, Mr. Hyde. And I think we caught everybody so far. Welcome aboard. It's been a busy week. So if you were with us last week, you may recall that we talked about some real nerdy physicsy stuff, because one of my friends who's here with us today, Unix Carbide, and I have been experimenting with some radio stuff and antenna stuff. And I said, gee, we should make a filter for these Meshtastic radios that we've been playing with. And I said, those little bitty boards with that little bitty radio on it. Yeah. Unix says, experimenting with equals going bonkers with. Well, okay, I'll admit that. But these little these little teeny weeny Meshtastic radio boards that we're using, they can't have awesome radios in them. And of course, I'm a little partial. I like awesome radios. So I said, gee, if we put a good bandpass filter in front of that radio, we might be able to improve performance by blocking out of band energy that you don't want. I mean, if you're standing in your shop listening to some wonderful orchestral music playing on, your favorite very expensive speakers, you don't want the lathe making noise while you're doing that. Oh, I said the word. Sorry, John. So that started a whole ruckus, and we talked about the physics of what goes on when you make things for electromagnetics, and we talked about skin effect and the fact that RF, actually any AC signal of current in a conductor is going to tend to flow on the outer skin of that conductor. And I just wanted to reiterate that a little bit because I don't know if I put it into perspective. In the world of RF, where things are like a gigahertz and above, that would be Wi-Fi 2.4 gigahertz, 5.8 gigahertz. This Meshtastic stuff that we're doing right now is 915 megahertz. So that will be, if you send that signal down a wire, it's only going to use a 0.005 of an inch of that wire for 65% of the current to flow. So if you multiply that by 4, you can call it, on the order of a 1,000th of an inch or less to carry all the current. Okay. Whereas at audio, if it was an audio frequency signal, so let's say you had a wire carrying audio to your Klipsch horns, that would require, you'd have to make a conductor over an inch in diameter for skin effect to start being an issue. So it's quite different. And anyway, so we started playing with this filter design, and I showed you some of the early designs. One of the things that I did as a way of studying the topic is I went to eBay. This was years ago. I went to eBay and I bought a couple of filters. These are called comb line filters because they have the fingers, as you can see in the thumbnail. They look like a comb. And I bought some and I ripped them open. And I said, let's see what the difference is between theory and practice, because these companies are selling these filters. Let's see how they make them. And I showed you some of those last week. Well, I use an electromagnetic modeling software package called CST Microwave Studio. And in CST Microwave Studio, anything you can describe in 3D, okay, and you can describe the material characteristics, you can model. And you can do this for filters, antennas, anything. You want to look at the radar cross-section of a crow. And again, anything you can model in 3D and get the parameters for all the materials you can analyze. So I started modeling the units that I purchased off of eBay, and I started getting some success. This is where the frustration level started ramping up, because I was getting very weird little behaviors in the model, and I couldn't isolate it, and I couldn't figure it out. And that's when I got sufficiently frustrated that I went back to the book, and the good book by Randy Ray, okay, called HF Filter Design and Computer Simulation. This is not a new book, folks. This has been around a while. And Randy gives an example of a comb line filter in his book which is made just the way we want to make it, made out of machined aluminum, etc. What he didn't do is he didn't say, here's a drawing, here are the dimensions. I had to go through that book word for word, or not the book, but the chapter, and pull out the numbers. I mean, literally, it took a lot of work to get all the dimensions, and then I modeled it, and I figured he built it, he modeled it, he measured it, he gave us the information. I should be able to duplicate his results. So this is what, I just take a minor detour here. This is what science is. Science is somebody does an experiment, gets a result, and gives you all the information you need to duplicate the experiment and duplicate the result. And if they do, then that takes your hypothesis and your theory and it turns it into scientific fact. So I was getting results, but I was getting results that were also frustrating. And I'm like, something's wrong here. And it finally boiled down to, he described the spacing of these comb elements, but he was talking about the spacing, literally the space between them, not the center to center distance between the comb elements. And I fixed that, and boom, everything worked perfectly. And I mean perfectly. It started duplicating what he did excellently. So then I said, okay, now I'm going to scale it to 915 megahertz, which is where we care about it. I'm going to start optimizing it. And boy, howdy, if you saw the lights dim in your house, it's because I was optimizing this thing like crazy. So we started getting some really nice results. And when I was all done, I had a filter. And if you look at the thumbnail, you'll see there's a little picture right there, little picture of the filter results that we were getting, and it was molto bono. It was excellent. So what happened was, that was me as RF engineer. Okay, that was me as RF engineer, and it was time to, make this thing. So how we're going to make it? So I had to hand this design over to the machinist. And that's how this whole thing started. That's how this whole topic started. Is in any organization or in any venture where you're going from some idea to some concept of how to make the thing to then finally making the thing, you're going through different processes where the goals are different. So the RF engineer had a really good idea and got to a point where he realized, at least in the computer, physically, this is going to work. And Carl, we could explain that in a minute. This filter, Carl's asking, what's the Q of your filter? So Q is an interesting calculation. The filter is from 902 to 928 megahertz, and we're showing about 1 dB of loss. And it's the steepness of the skirts which determine the Q. And I'm not ready to talk about that today. So you and I could talk about that offline, maybe in the after party roundtable. So the engineer has a really nice design, and the engineer hands it to the machinist. So the machinist sits down and looks at the design and starts figuring out, how are we going to make this thing? So we had to make a couple of compromises. Oh, so the engineer, when the initial design was being optimized, was using a material called PEC. And by the way, if you have a McMaster car catalog, you might want to look up this alloy. It's called PEC. Anybody know what that stands for? Anybody familiar with this alloy? Anybody? Carl? Nothing? Papa Echo Charlie. Oh, I know you're going to know it. Come on. That's exactly correct, sir. Perfect electrical conductor. So the initial modeling, of course, was with perfect electrical conductor. So one of the things that the engineer realized is that we have to actually make this thing. So as RF engineer, I modeled it in pure silver because from a practical standpoint, it's the best conductor we could put our hands on. And if we want to, we actually can silver plate everything. So in this, in the prototyping phase, I don't think we're going to spend that much money, but yeah. And Protium says it's not like silver is at an all-time high or anything. You are correct, sir. Well, okay. But to be fair, how much do you need? You need 1/1000th of an inch plating. So it's not really the silver cost itself that's driving it. So here's the numbers. I'll give you the numbers. The loss in band, inside the filter band, which is what we kind of care about to make this thing not detrimental at any point. It was, let's see, I have the numbers right here. The center band loss with perfect electrical conductor was 0.07 dB, minus 0.07 dB. Okay? The center loss with silver was 0.75 dB. Now, 0.75 dB is not too bad. Then, switching it to aluminum, from silver to aluminum, it went to 0.98 dB. That's a difference of about 0.2 of a dB going from silver to aluminum. Okay, so aluminum sounds like it's not such a bad idea. However, because this thing's made of multiple parts, some of the parts are going to be bolted together. And that is not a continuous piece of aluminum. So now there's a possibility for those losses to go up. So the engineer hands this thing over the wall to the machinist, and the machinist starts looking at it. And the machinist says, well, first of all, we have to make this thing a little bigger than you thought because we need room to put a bunch of screws in to squeeze the two halves together. So we're going to make it a little bigger. And not only are we going to make it a little bigger, we're going to make it a standard size or close to a standard size. So in this case, it turned out that the bottom half of the filter can be made out of 1 1/4 by 1 1/4 aluminum. So the engineer says to the machinist, hey, I got an idea. Let's make it out of 2024 aluminum because that's got copper in it and that's got to be good, right? So the machinist goes to the McMaster car catalog and says, well, how much does 2024 cost with respect to, for example, 6061? Oh boy, were they getting a 3x premium. So it turned out that 2024 maybe wasn't the best idea. So the machinist and the engineer agreed that for the first prototype, we're going to make it out of 6061 and go from there. Protium Machining says, what affects it more, a bolted connection or a welded connection and the warp from that? So this is a really great question. Let me just zoom in a little bit on this little piece of the model. So what Protium is saying is, down here at the bottom of one of these comb elements, we're showing the prototype as being bolted in. And what if we welded that? Well, if you look at the top of the element, there's a pretty close fit. There's air here between this element and the upper housing. There's a reason for that. We'll talk about that in a second. And then there's a tuning screw that comes in from the top, and there's air around that. So if that element warped, it could be bad. The worst thing is a short. The second worst thing is making it so narrow that you've lost the ability to stand off the voltage that you're going to generate. So I don't think we want welding in here for exactly the reason you're pointing it out, that you're going to get some material warpage. So that's no good. So we're going to make it at a 6061. Now, in full disclosure, what Randy Ray did in his book is he made the vertical posts not out of aluminum, out of brass, and then he had them silver plated. And his argument went as follows. He says the bottom part of the structure can be aluminum because the current density is very low, but those posts have to be very low loss, and that's when the current density goes up. So they're going to make those out of silver. So he had a dissimilar metal between silver and aluminum. I wasn't too thrilled about that. So I decided that to keep things simple, we're going to make it aluminum. So it'll be an aluminum contact. I hear you screaming, Dale. So hang on, we'll talk about that. And we're going to bolt it. And that's the bolts you see in the bottom half of this picture. But wait, we're getting ahead of ourselves because we have to talk about the size of things. So the machinist looks at this and he says, let's look at these dimensions. Well, these days, when the engineer heaves something over the wall to the machinist, it's usually a 3D model right out of the modeler, right out of the electromagnetic modeling simulation program. And the machinist looks at them, and they're all these oddball sizes. There's 4 decimal places on them, and there's nothing standard. So machinist goes back to the engineer and says, listen, we need to, if we use standard sizes, we can build this thing at a lower cost and a faster production speed. So the RF designer says, well, what are the standard sizes that we can use? So together they go back to the McMaster car catalog, and they find out that these rods that the elements are made out of are a little bit smaller than a 5/16 inch dimension. And McMaster car has precision 6061 within 1,000th of an inch of diameter, and good surface finish, ready to go at a small premium over the normal stuff. So the machinist says to the RF engineer, if you make it at a 5/16, we won't have to turn the outside of this thing. Can you do that? And the RF engineer says, I think we can do that. The second thing that happened was and you have to look very closely at this picture to see the difference. On the left side, the tuning screws were made out of 256 hardware. And if you've ever played around with 256 hardware, you know it's very small. It's very flimsy. So the engineer, the machinist says to the engineer, can we make those bigger? And hey, I have another idea. What if those those little holes that those tuning screws are going into are the same size as the tap drill for the screws at the bottom. In fact, we can make that part completely symmetrical so that it's the same drill that drills the top and it drills the bottom. The RF engineer, recognizing greatness when he hears it, says, I think we might be able to do that. So it turns out that they worked together and they came up with this idea. If we make the tuning screws 440 and we use the same drill size, which is the 75% thread drill for a 1024 screw thread, you have about the same clearance between the tuning screw and the post as you did before, except it's a 440 screw, which is a lot nicer to deal with. The vertical post becomes completely symmetrical, which becomes an L word part. Okay, I'll say it, lathe part, and that's going to work pretty good. So that's what they did, and it came out. You could see the third post from the left, the one that's blue. That's the final design, and that looks like it's going to work out really well. So the plan is a long set screw in 440. It can be stainless steel. Why can it be stainless steel? So the machinist goes to the RF engineer, can I make this stainless steel for the screw? And the RF engineer reassures him, yes, you can do that because this is a very low current part of the circuit, but it's very high voltage. So that's going to be a stainless screw, and then a grub screw can go on top of it to either close off the hole or actually become a jam screw against the second, against the tuning screw. Okay, Evils asks, doesn't that mean you're tapping the top of that post for no reason other than not having to pay attention to orientation and so on? So no, it's not going to get tapped. You overinterpreted my use of the word symmetrical. It's not going to get tapped. It's going to get drilled the same way, top and bottom, but only one side is going to get threaded. Does that make sense? I hope that clarifies it. So now we're down to, well, I see 1, 2. We see the tuning screw, the grub screw, the screw downstairs, all McMaster car parts. The post is going to be a precision 6061 rod, which will get faced, drilled both sides, tapped one side, and then again, pretty straightforward. So now the machinist is starting to get happy, right? This is completely doable. The RF guy says, yeah, this is a good for a first go around. And now we come up to one of the challenges that face them. And one of the challenges is right here at the bottom. Let's see if I could point at it. Right here at the bottom where the screw pulls that rod into the bottom housing, that is a high current point, and that wants to be a very, very good electrical connection. In a perfect world, we would want that to be a not a joint at all, okay? And in the end, if this design proves valuable, this whole thing could be machined out of a chunk of aluminum without the rods being separate. But it's too much of a reach for the first prototype. But if that becomes necessary, then that becomes necessary. So Evil says, why not press fit it and then weld it? Well, welding it is out of the question because the time, I mean, the RF engineer asked and the machinist said, yeah, A, you're going to get the distortion. B, it's going to be very difficult to do a good job welding at the bottom of that cavity. So you've just increased your costs tremendously, and you've increased your ability to get to P1 by a lot of calendar days. Okay, so Evil says, no, weld it from the outside. So you have to make believe you're a piece of current. And if you're flowing down this rod, you want to go right out to the surface of this well. So let's say you didn't have a good connection until you got to the bottom of this rod. You would end up with some losses and some problems. So we talked about this, and we talked to some outside people. I'm looking at you, Dale. And there's a bunch of ways to get that aluminum to aluminum connection pretty good, and then the pressure of the lower screw is going to be pretty high, and I think we're going to be able to do it. It's going to be good enough for the first prototype, and because we've simulated what the losses should be, if the losses are significantly higher, we can assume that some of those compromises is where the losses are coming from. Sleeve it. Mr. Tim Beatty says sleeve it. So there's a bunch of tricks we can do down there. And I've thought about, believe me, I lost a bunch of sleep on this. And right now, I think the procedure is going to be, oh, I should point out also that the location of the rod, what the RF guy keeps calling a resonator, it can tolerate a couple of thousandths of an inch of slop. So it's not that the rod position is hypercritical. That's important to know. So the screw, as shown, is effectively locating the rod. Now, using a screw to locate something is not a great idea. By the way, keep that in mind because there's something coming up. But in this case, it's okay because the screw hole, the clearance hole for the screw is a tight fit, and the allowable motion or position of the rod, it has a little slop in it. Yeah. John Thawley says, love all the abstract third-person dialogue. Personal pronouns are so over. Listen, this is potentially, schizophrenia, I think, because I keep talking to myself and I keep getting answers, and some of them are good. So we're just going to roll with it for a while. So that's how we ended up with the design of redesigning the rod. Now, the thing that happens as soon as you do that is the RF engineer now has to go back and re-optimize the design for the new numbers. So now it's going to be 5/16 inch rod. Now it's going to be 440 screws. And off the simulations went, and it worked. I mean, the design came in for a landing because we weren't that far away from optimal. We made some adjustments. We went back to the RF engineer. RF engineer re-optimized, and everybody's starting to get happy and excited. So the design is working. Proteum Machining says, if you're not talking to yourself in the shop, you're not challenging yourself. I guess I'm challenging myself. So in going back to the optimization in the RF simulation software, we came in for a landing and have an electrical design that works super. Okay. The next thing is, okay, how do we finish the design, the mechanical design of this? So this has a sort of a top section as well as the bottom section. We've been focusing on the bottom section. Well, the top section now is going to sit on top. This does have an alignment thing where it wants to be as closely aligned as possible. And also, not shown here, it's going to be screwed around the periphery so that the top and the bottom are screwed together pretty tightly. And you might notice that at the split line, there's another rather large aluminum to aluminum connection. So the RF engineer says to the machinist, is there any way we can make sure these two sides, when they go together, are very, very flat? Can we make them very flat? Of course you can. If we have to, we could just hit it on the Lapzetti plate, or we could hit it with the PFG stones. If necessary, we could do both, and we could also surface grind it. Believe me, we can get those two pieces very, very flat. Yeah, Proteum says the short version of that is, how much money do you have? So that's what we're going to do. We're going to make sure that they're very, very flat so that connection is as good as it can get. The other thing we're going to do, and then I want to go back to aluminum, is in addition to a periphery of multiple screws to hold it together, we're going to have two locator pins. So there'll be two precision holes, both on the top and the bottom, and we'll drop in a couple of little pins and we'll put them together, and those pins will align the top and the bottom. We're not depending on the screws for alignment. We're depending on those pins for alignment. Because remember, the capacitors, that's what they are at the top, the airspace between the top of the rod and the top section is effectively a capacitor. Those capacitors have to be aligned well. So that's what we're going to do. We're going to have a pin on opposite sides of this long structure, two of them, and that's going to align the top and the bottom. And then a whole bunch of screws around the periphery. So the machinist says to the RF guy, is it okay if I add some material to the outside perimeter? And the RF guy says, outside, I don't care. Yes, you can absolutely do that. The machinist says to the RF guy, have you thought about how you're going to mount this thing in a structure? And the RF guy stares at him blankly and says, no, I did not. He says, well, what if we add a couple of screw holes that you can use to mount this thing to the structure that it's going to be in? And the RF engineer dumbfoundedly looks at him and says, that's a great idea. So there's going to be additional threaded holes so that this can be screwed to a bracket or whatever. Finally, one design element that we have not yet settled on is the connectors. So stay tuned. That's going to be coming later. But right over here, where you see the abstract input port, okay, we don't have a connector yet. So we haven't picked the connector, and the connector is going to be part of the equation, and we're going to have to make that work. Okay? So that's the disclaimer of what we haven't done yet. And the really good news is that the RF engineer took the machinist out to lunch, and they're getting along fabulously. So that's working out pretty well. Yeah. Evil says, connector, just solder the coax to that in the field and seal it with caulk. Yeah. Get out the aluminum solder. I actually have aluminum solder. Topic for another day. So let's talk about these aluminum to aluminum connections. Has anybody here ever seen aluminum? Anybody? Every morning in the mirror. So, yes, we'll bring that up. Yes, we'll bring that up. I'm getting all sorts of good ideas. So if we take aluminum, let's say you take a cutting tool and you cut a piece of aluminum and you look at it. How long is it before you're no longer looking at aluminum? And the answer is microseconds, because aluminum, oh, there it is. Live aluminum from Brooklyn, New York. Plate Pringler says, I only machine the British pronunciation of aluminium. Listen, you could pronounce it any way you want. It's not going to change the physics. And the physics are that aluminum is the most reactive metal you ever encounter. So if you cut a piece of aluminum and you look at it, you're already late, okay? Microseconds, no. Evils, nice try. Aluminum is more reactive than magnesium. So the very act of aluminum reacting with oxygen so quickly. Oh, yeah, you looked it up last time. No, it's not. Wave your fist in the air now. Go ahead. If you pick up a piece of aluminum, here's a piece of aluminum, okay? And if we take a torch and we try to light this on fire, it's not going to happen. And the reason is that the aluminum creates, when it oxidizes, creates what? That's correct, grinding wheels. It creates grinding wheels. It creates aluminum oxide, which is very, 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 very stable, okay, and very non-reactive. So aluminum is wonderful for that, and it's also horrible for that. So if we take two pieces of aluminum and we try to put them together, we are inevitably putting aluminum oxide against aluminum oxide. So there's tricks. One of the tricks is to put it under oil and abrade it against each other, or gall it against each other, and you can get the aluminum oxide to maybe get out of the way under oil, and then if you keep the pressure on, you maybe get a let's see, the reactivity series. You'll have to just interpret that for me there, buddy. Is solder low enough temperature to bond them without distorting the pins, says Protium. Possibly. So I have some magic flux and solder. Now the solder is not magic. It's called SN100, or tin. It's basically a tin, mostly tin with a pinch of herbs and spices. And that plus the flux that I have soldered aluminum. Question is, what's the resistivity of the solder? Okay, good question. Don't know. I'm just reading everything that everybody's typing. So Dale suggested galling under oil. Okay. Frankly, galling just by itself, just abrading the two pieces together might be enough. So possibly rotating the post while tightening the screw might be enough to just do a good enough job. At the end of the day, there is one thing that saves us, and that is that if there is aluminum oxide, and we do have two pieces of metal with aluminum oxide, and the surface area is big enough, and the layer between them is small enough, it acts like a capacitor. And at RF frequencies, that's probably good enough. So we won't know. It's going to be an experiment. We won't know till we know. And if the computer, if the RF engineer's simulation computer says that we can expect 0.98 dB of loss through the filter, call it 1 dB. If we're getting 3 dB through the filter, it's probably due to those losses. If we're getting 1 or 1.1 dB through the filter, hallelujah, it's good enough. Okay. So Protium says a very, very wise thing. He says, I guess the real question is, how much work are you going to put into it if the plan is likely going to be a monolithic part? He says eventually is going to likely a monolithic part eventually. So the answer is, it's likely, we don't know. So if this thing has commercial value, in other words, if it has a market, by the way, the marketing guy was not in the room at any time, but if the thing has a market, it might turn into a monolithic part. And that all these questions go out the window. Okay, that's a really good question. But for now, it's P1. So if it has some loss due to the aluminum oxide in those connections, that could be a lesson good enough for P1. Also, Robin says allodyne. So there is a mil-spec coating that is variously called things, but allodyne is a commercial term for it. And I've used it. Do I have I don't know if I have something. Yeah, I do. So when you see a piece of aluminum that has a nice gold color to it, that potentially could be what we're talking about. Josh says, I use allodyne at work. There you go. Protein Machining correctly says MIL DTL 5541. You guys are awesome. So this is an antenna that I designed and built, and this has an allodyne coating. So allodyne to allodyne has potential. Little joke there. And we'll see what happens. But we're going to go ahead and the first one, P1, is just going to be aluminum, and we'll see what happens. Carl Tauber asks, have you designed the antenna for the front end? No, it's a separate problem. So we have some antennas in mind for some of the applications that we have. So the answer is no. The antenna that I just showed you, by the way, is a potential directional antenna for that same band. So you can't swing a dead cat around here without hitting an antenna appropriate to the task. So, once again, we visit the aluminum electrical issue. Somebody said, what about use NOAA locks? So NOAA locks is a very good example of a product that is commercially available, and it was designed to deal with aluminum to aluminum electrical connections. I don't know that it's... I will look at it. I don't think it's super applicable here, but it's worth looking at what is it supposed to do and what is its mechanism of action. Maybe that's a useful thing. Irregardlessly, and hereby notwithstanding, the connection between the top half and the bottom half of the housing is big enough that I'm not concerned about it. So that part is not where my concern lies. So yeah, we'll see. We'll see what happens. So the machinist goes off and finishes working on a mechanical design, and is now going to go back to the RF guy and say, okay, take a look at this. They're going to communicate. They're going to communicate. He's going to say, take a look at this. All of the internal dimensions, everything we talked about is exactly the numbers that you optimized. The external dimensions have been increased. Are you okay with this? And the RF guy is going to look at it and nod his head up and down and say, I think we're good for prototype. Let's do it. And the parts get made. There's a few other details in here that have to be worked out, so I don't want to dwell on the minutia, but I think you get the point. So, I've talk about making prototypes. I have some stories, but I think we'll wait on that. One of the big problems in companies and corporations and engineering chains, from the idea guy all the way through to the guy who's making the product and then the guy who's selling the product. One of the things that is often a problem is two-way communications. And in a lot of situations that I've heard in talking to people, there's one-way communications. And this is not good. Because just in this little example, we've seen that cost was affected, performance was affected, speed to the prototype was affected, ultimate production cost is affected. There's a bunch of things that matter here, and the machinist can turn around and talk in the upstream direction and say, listen, there may be a better way to do this, and the RF guy should listen to the machinist. Now, when I say machinist, I recognize that in a lot of organizations, there's a possibly a mechanical engineer and possibly a mechanical designer. They're not the same people sometimes, okay? And then from the mechanical designer to the machinist is usually the connection. And I've worked with some great designers that made their job to understand that interface. And I recognize that. So when I say machinist, I'm really putting a big umbrella over a couple of different functions. But I think it's so important that that two-way communications occurs. When I was, working for companies and designing things, we frequently had engineering design reviews. And in fact, in aerospace, it's very formalized. Preliminary design review, critical design review, blah, blah, blah. But we'd have design reviews, and the number of times that the production people are in on the design review is very few. That's a mistake. The people producing the stuff should be in the engineering design review. They may have almost nothing to say, but if they have that one thing to say, it's pretty important. I remember once we had to do a prototype of an antenna array that I designed for a company. I'm not going to get into those details. And the engineering manager said, "Oh, I got this. I'll." And they wanted to take a cosmetic model to a show. He goes out and he buys a piece of Delrin that was, I swear it was 4 inches. It might have been more, 4 inches thick, about, 30 inches by 30 inches. Does anybody want to take a guess on how much that piece of Delrin cost? Then he hands it to a machinist, and he gives the machinist a drawing on the back of a napkin, and he says, "Here, do this." Well, the do this was hollow out almost all the material to make something which should have been made by vacuum forming. And it was a terrible idea. And it should have been two-way communications. All right. So those are some details about a project underway, about an engineer and a machinist actually communicating. And this thing's coming together. So stay tuned. We'll show you the results of this thing, because I think it's going to work. I think it's going to work pretty well. I see Dale typing furiously. Let's see. Yeah, Prodium says, that's because the marketing guy was already out promising a perfect antenna to his customers. Yes, he was. Oh, so, okay, Prodium. I was at another company, and I designed an antenna, and we built some prototypes, engineering prototypes for internal use only. Engineering prototypes for internal use only. And it was a little antenna, it was a plate, and it was a patch antenna with a unique sort of feed arrangement. And then a little machine Delrin housing. And we made a few of these. We probably made 5 of them for engineering use only. Here we are now, fast forward, 3 years down the road, more or less. And I am talking to a government organization. I am in a internal space, let's just say. I had to have clearance to be there, and I'm talking to the potential customers about some things. And they said, "Oh, you're an antenna guy." And I'm like, "Yeah. Do you ever see one of these?" And he reaches down and he pulls out that antenna. And I start laughing. And I say, "Yeah, there's 2 things you should know. Number 1, I designed that. Number 2, that should never have left the company." Okay. So many stories. Yeah. So Dale says, how would I make any money if the engineers didn't request crazy stuff? You should hear some of Dale's stories because the engineers request crazy stuff and they didn't ask Dale first. And Dale's like, yeah, I can do that. And here's what it's going to cost you. And sometimes they say, okay. Dale goes and he does it. Come to the after party roundtable for some of those stories. All right. I have another prototype I have to make. And Mr. Unix Carbide, are you available? If you can show your face, we'll talk about this. I have to make a stand for illuminating an optical flat for the big stuff that I'm doing. So I have an 8-inch optical flat. I have 6-inch parts. My idea was to build this stand. Originally, I thought, I'll make this out of 1x1 steel. I'll weld it up. And I have a beam splitter I have to put in there. I have to have a mount for a camera on top. I have to have illumination coming in from the side. So there's a bunch of stuff to illuminate and put into a camera the optical flat and the part that I'm evaluating. And it occurred to me that maybe there's a different way to do this. So I wanted to spend, I don't want to spend a lot of time. I'm going to spend about 10 minutes talking about another approach that I thought of, and that is to use some of this stuff. Now, a lot of you are familiar with this stuff. This is, you might know it under the brand name 8020. You might know it under some other brand names, but this is basically an aluminum extrusion that has become a real, boon to prototyping, low volume production, and it comes in sizes ranging from, I guess this is 20 millimeters by 20 millimeters, and it goes up to pretty big stuff. And sometimes you see, big structures made out of it. And I think I'm going to make this stand, this illumination stand, out of this stuff for a couple of reasons. Number one, it might be fast. It is reconfigurable, and others have done it. So, can you turn off your fuzzy background? Is that okay? So one of the folks in our group is Mr. Unix Carbide, and he has built or is building a 3D printer, and the entire structure of the 3D printer is this stuff. Other people have built. I think Stefan Gottsventer is making his or made his CNC gantry mill out of this stuff. So I want to talk about this a little bit. Robin says, Automation Direct will cut pieces to your list. Excellent. I like to hear that. Proteum says, so will Misumi, and drill tap the ends if needed. And on that note, I'm going to bring, you're muted. You could turn off your muting. I'm going to bring in Mr. Unix Carbide. Hello.
Hi. Good morning. Good day.
So you're partially responsible for me to decide to do it this way. I did one little.
I'm sorry.
I did a little tiny frame with this stuff to hold those brass sheets in the laser, and it worked out great. And so you've been coaching me on this, and go ahead, take it away. Give us a quick overview of what you've learned.
Yeah, so I came to learn this stuff. Look, I'm not an expert on this. I've just done a bunch of it, and I've screwed some stuff up along the way. So I'll consider that good learning. What is this stuff? I came to it in the 3D printing world. People build 3D printers out of this stuff, which is 2020, which means it's 20 millimeters by 20 millimeters. Throwing this up at the camera here. And this extruded aluminum allows you to put T-nuts in the sides, which can either be slid in from the ends, or there are drop-in style that kind of curl in. There's kinds with little springs on the back so they don't slide around. There's all manner of fasteners. In the 3D printing world, just about everything gets built out of this 2020 aluminum extrusion. I started building a printer with specific precision aims and certain rigidity requirements out of what is 4040, but still the same 20 millimeter base. So the slots are the same size, but the extrusion's bigger. They make stuff that this gets into what seems to be standardized nomenclature, and it kind of is once you get used to it, but it's not always standard. Where you could get extrusion like this that has a gigantic T-slot in it, a single T-slot for much larger hardware. Like it gets into all kinds of, this is what all the kids who grew up doing erector sets did as adults, right? Like, oh, let's go crazy with this stuff. So I started building a more stout printer, and there's all manner of other obtuse sizes in between, like this, which is a 20 by 40, etc. So you can get all kinds of shapes for the base stuff. Spencer, you had asked before, how do you attach it? What do you do? You get some drywall screws out of an old project bin or something you did in the garage, and you just go until you.
Okay, hey, thanks. Thanks for playing.
Hammer mode. Whatever. No, the most common way of doing this is a thing called blind joint. It's the most cost-effective because there's not lots of extra hardware. It's also the most rigid because there's not a lot of extra interfaces of hardware. And the blind joint basically means that you put a screw in the end, pretend I just did that, and you slide it into this slot whereby you will have already drilled a hole here that you can get a Torx or hex wrench through to tighten it against the part. Done. That concept is very easy.
Question.
And it also means that you don't have to drill precision holes. You need a hole that's big enough to get your driver through.
So is this is this kind of a hole recognized by the guys that will do the cutting? Like Robin says, Automation Direct will cut, Misumi will cut.
Absolutely.
Okay.
I have not done anything with Automation Direct. I've done stuff with Misumi, and I've done stuff with 8020, and I've done stuff with good old eBay offcuts. My experience has been the Misumi stuff is super well regarded as being the awesomest in the printer world. Is that true? Well, I haven't done enough of this for enough years to actually know or care that much. I have used Misumi because they do publish specs on tolerances, so you can get precise cuts, which at the end of the day, from what I've experienced ordering stuff from them, looks to me that non-precise cuts, which cost less, are saw cuts, and they're very good. And the precise cuts have been faced with the mill and, cleaned up. Do they meet the tolerance specs? Yeah, close. Yeah, pretty good. Yeah, sure. They can also do Automation Direct, 8020, Misumi. They can cut everything to whatever spec you want. There's a cult around Misumi stuff that's kind of cool, that there's these one-liners that are like a specification of the order of which numbers you put in which place, where you can do really big, crazy orders just based on these one-liners of like,
well, you like
this extrusion, these cuts, these holes here, et cetera, et cetera, et cetera. And some people know that shorthand like the back of their hand, and it's kind of like people who, know raw G code for things. Let's
just admit it. You like code, so this fell right into your.
I do.
Into your brain.
I do. Yeah. It looks like a log line to me. It's very, very appealing, but the very parsable, very, very straightforward. But the Misumi stuff is also expensive. So I have had the unfortunate problem of screwing up my own order, and that's
Yeah.
that. Reuse the extrusions elsewhere, but yeah, it's no fun. One other thing about the end, Dale was actually cool with this. If you're going to reuse, or if you're building a mechanism that you're going to take apart periodically, tapping the ends that you're going into first is a great idea. And this aluminum, being aluminum, you can use form taps if you keep things jigged up and clean and straight.
So you
To
mean
great effect.
as opposed to using the self tappers?
The alternate is, and there's lots of self-tapping hardware you can buy, and the self-tappers just go in the end, and they're if you're going to remove things or adjust things often, not the best. One other thing about some of the hardware you have to watch out for is if you try to build something that's precise, like I have been with the printer frame, the hardware sometimes have these wonderful little barbs underneath I don't know what they're actually called, underneath the screw head. Look at your hardware and consider what you're doing first, is what I'm getting at here. Because those have proven to be giving me a great amount of trouble, to the point that I've now, taken a diamond file and sawed them all off on a bunch of parts, because those little barbs were moving my extrusion as I would tighten them down to spec. For other applications, they could be just what the doctor ordered, right? They're going to be fast and solid, and they're not going to go anywhere.
So let me ask you this: if I'm building this project, which is basically a vertical stand, it's going to look like a night table, kind of tall, and I want a very nice frame, and then of course I'm going to be attaching things, and my idea is that I'll be designing things, 3D printing the widgets which are going to attach to the frame to hold, the glass reflector that's going to hold the camera mount and that sort of thing. So there's going to be a marriage here between the.
So obviously you want your tolerances for this frame to be 100 microns over, say, what? I don't know. That much, right?
I haven't thought about it enough to put a number on it.
No, you don't want that kind of precision.
Yeah.
I would use self-tappers for what you're doing. Absolutely.
Okay.
Because, if you have a variance of a 0.5 millimeter at one part, it's not going to affect what you're doing with this. And the rigidity and you're using this stuff for other properties, the rigidity, the ease of construction, all of that. Self-tappers are the cheapest option and very straightforward. I would also say, with anything self-tapper, go for the Torx heads. Don't screw around with hex heads.
Okay.
Strip those things out. Like the Torx. Torx is good here.
Okay.
You do put some torque on these things when you're self-tapping. But the also I found Never Sees is the bomb with self-tapping as well. Really, really cool. Little dip, little wipe. Just right in.
Mr. Tim Beatty says it only has to last until it tips over. You're making me a little nervous now, Tim. Just saying. I think we'll be screwing it to the bench.
Also, one more thing for your application. I don't know if you already got your stuff, but I'll just throw this out for other people thinking about similar applications. So I mentioned the vendors. Robin mentioned the other vendor, which I would love to try them sometime in a project. eBay. So there's a lot of people doing stuff with extruded aluminum and sell all the offcuts. So if you're doing a project and you don't care that it's anodized purple and that you're going to get some weird cuts because you don't quite know which size it's going to be anyway, you can get away with buying this stuff for nothing if it's anodized purple. And it's not always, I say that jokingly, it's like most commonly it's clear and black anodized. So it's not like purple's really gonna, but purple's real cheap. We find it. So basically that's one of the kind of cool things about this, is that there are so many industrial uses of this stuff that buying offcuts, if you have things like I would say the bare minimum for working with this stuff and cutting it yourself would be a chop saw of some kind. And I mean like a woodworking circular miter saw, right? Throw an aluminum blade in there. You're done. That's your bare minimum to getting a bunch of work done with this stuff. Not precise, but good. And then moving up the stack, a mill. Just having a mill, and you can now build really precise things. One other thing about some of the nicer companies, so 8020, Misumi, and I'm assuming Robert Spender too, they publish things like torque specs, right? So if you're going to do a blind joint with this fastener in this hardware series, your torque spec should be between, like I know for my stuff, for these big guys and the M5 self tappers, I know that it's between 9 and 12 Newton meters. Cool.
Got it.
Like that, like little, it's those little things that make quality of life and speed to getting the stuff together worth it when you're buying it from the guys.
You mentioned Torx drivers as a something to have around. A chop saw would be really nice to have around. A mill would be really nice to have around. I don't think that's a problem. Are there any other tools that you recommend?
Drill press. I mean, if you don't have a mill that you putting the holes in, a lot of the things like the blind holes could be done very, very trivially with the drill press. I would say I did it in my little teeny micro shop here without a drill press with jigging and craziness, and I wish I had a drill press.
Yeah. Okay.
Would have made it faster.
Hey, Robin, did you want to add anything to your? Oh, he disappeared. Robin disappeared.
Oh,
he had to go.
One more comment on what's possible with this stuff. I published some specs. I'd have to find them in old chat, but it's in the PFG Discord on throwing these up on the surface plate with the nice, 1 micron DTI and going bonkers with all the heavy gear.
Mm-hmm.
This stuff is shockingly flat.
That's amazing.
It's shockingly straight. It's shockingly square. So as much as this stuff gets used for, things that are basically like, hey, we're making a glorified coffee table for an industrial use. This stuff could be used and utilized for all manner of precision applications. It's actually pretty spectacular on that front.
I think I've seen optical bench type stuff that was built that way. So clearly it was good enough for that kind of stability. So, okay. Well, I'm looking forward to leaning on you a little bit because I think I'm going to do my design. Oh, well, that's another question. How do you do your design with this stuff? Are there tools?
All the specs, all the companies. I mean, here's one of the neat things, how I do design, but it's a neat thing about this stuff. This is 40 millimeters by 40 millimeters dead square. So I make 40 millimeter rectangles and elongate them and do my design. Done. Like I'm not gonna overthink it. When I've done stuff like these were for some of the pieces that I ended up filling with a mix of lead and rubber crumb.
Yep.
So how do I get that shape so that I can print a little thingy to go in there to cap the end with some silicone? Well, the 3D CAD files are all online for every single brand imaginable.
Wow.
The cheap stuff, the nice stuff, everything. So I just grabbed it, copy paste, print one, hopped right in, so basically however you want, whatever you need to do. But the real gist here is that this stuff was designed so that you're not actually fiddling with getting the exact dimension of this opening and worrying about how just working with a rectangle.
Yep.
It's yay long. And I'm going to stick it to another one, yay long. Done.
So we're getting some commentary. Protium says 8020 has a builder app on their website. Interesting.
Absolutely. Yes.
Eric Moore says
they all pitch different softwares. Yep.
Eric Moore says McMaster has 3D models too. And Paul says McMaster has a decent selection as well if you happen to be placing an order anyhow. McPriced per usual.
Now, okay, I'm going to say something that could be construed as controversial in here about all of this.
Yes.
I have ordered.
You're not going to tell me I could put this in a lathe, are you?
No. Absolutely. But I'm gonna mention one of the least favorite vendors around here, which would be AliExpress. The stuff that I've received from McMaster was exactly the same chromed garbage that I ordered from AliExpress. The difference was McMaster had it to me within 24 hours. AliExpress took 5 weeks. The cost difference was profound. So this stuff is so standardized and so boring and so cheap. This stuff is not made in the USA, a lot of it. And if you find stuff that is, that's wonderful. But as far as I'm concerned, I have not found discernible, measurable, traceable, or otherwise advertised quality differences in much of the actual ancillary hardware.
So
period.
I'm going to say something that is may also be controversial. If you're making something and you need it made and it's engineering and it matters and you want to get going, just order from McMaster-Carr. You know, one of the things that we complain about sometimes is some of the things are more expensive in McMaster-Carr. But you know what? If the thing you bought from McMaster-Carr is junk, you're going to have a refund in 27 seconds. And that, I think, is one of the reasons we really like McMaster-Carr is their customer service. So, in fact, the piece that I was just playing with, this did come from McMaster-Carr. And, you know, I ordered it, I had it, and it's not a problem. So, yeah, if you're going to do a lot of it, I could see going for some bargains. But, boy.
Well, there's two. I would actually argue there's two cases for this, Spencer. If you do a lot of it, yes, going for bargains and sourcing it. But second, if you have a sufficiently large project, like my printer, I've been working on this for 18 months longer.
Yep.
It's a personal, fun, passion project. Like, this is not what I do for a day job. I'm having a blast. It's large, complicated project encompassing all manner of different technologies and materials that some of them are brand new to me. Right. And so when it comes down to it, do I actually care if it gets here in 5 weeks? I may not even be to that part of the project in 5 weeks. Right. So there is some calculus like that goes into it. The second part is if the thing arrives and it's garbage, if I go to McMaster, yeah, I'll get the refund, but now I got to spend time doing that for a small part. Whereas, and I might have spent like, I don't know, $35 on a bunch of T-nuts, and I got to work with them on it. Fine, they're easy, they're wonderful, they're great to do this with. On the other side, if I spent $3 on the same bag of thing, and that's the kind of price differential we're talking here. It's really, really huge gap. If I spent $3, they arrive and I'm not going to be using them. Do I really care? Do I get to throw them in a drawer for different use down the road?
It's a good trade-off.
I don't care. Yeah.
So Paul also says Amazon has some stuff that's fine. Aluminum corner plates and corner braces have been okay at a decent price. He says he agrees with you on T-nuts. Seems to be all the same, but toss the bolts and buy quality Allen/Torque from McMaster.
Always.
Yeah.
Yeah. But I'm a big fan of Bolt Depot for all my nuts and bolts and a lot of stainless in the shop. And wherever you source your stuff that is good and known good to you, nuts and bolts. Yeah, nobody has time for junk.
Well, thank you, because I have to get this this thing going. I don't know what we're going to call it, a frame, illumination frame, fringe imager on the fringe. There's a lot of fringing going on. Mr. Unix Carbide, thank you so much. I appreciate you.
Yeah. You need to definitely go on eBay and get some like lace fringe.
Yeah. Okay.
The viewing area. Yeah. So that you keep the fringe theme, All
right, bud. Thanks for being there.
Thanks.
Catch you later. Well, yeah, that was absolutely awesome. Thank you so much. And we'll keep you posted on that particular project, but I wanted to just show you what was going on here in the shop. And that's the engineer I got to build a thing. I talked to the machinist, and the machinist said, you don't have to start cutting and welding, and let's try this stuff. So we're going to try this stuff. Okay, I think we've done it, and we're going to bring this thing in for a landing. Thanks for being here. Let's see. Let's check the calendar for next week. Oh, I wanted to point out that I do recognize that it's the day before a federal holiday, and usually the PFG.Live, we take a day off for 3-day weekends. I didn't do it this time because I wanted to get together with you guys. But tomorrow is Martin Luther King Day, and I would encourage everybody to spend a couple of minutes thinking about that, and think about what he did and what it means and why we're taking a day in remembrance of Martin Luther King and civil rights. I think it's important. I think it's appropriate, and I think we should do it. Oh, there's Unix just posted some good stuff. We'll have to look at it in the after party roundtable. In other notes, I think we got everything. Anybody have any community notes that we might have missed? Okay. Thanks for letting us go over today. I enjoyed giving you guys the inside scoop on what's going on. In the meantime, if you need something to make something else flat, head over to PFGStones.com and read up. I did some modifications to the website, nothing major. Oh, there's one piece of news. We have gone out of stock on the Sensorion temperature humidity boards. Sensorion has changed the design. It's no longer available as it was, and I think they said April for their new design, their little board. We have something in the works. I don't know if we can get it productized in time, but we're going to be out of stock on that for a little while. I think that was the only major news that I needed to give you. But we'll look forward to seeing you guys next week. In the meantime, get flat, stay flat, and we'll see you next week.